Okay, so in this problem, you're in an elevator and you wake up there, and instead of having lights that show you what floor you are on, this elevator only shows its acceleration on a screen. And suddenly the elevator begins to move. You feel lighter, and the screen reads that the acceleration is negative 2.10 meters per second squared. So you know your mass as 58 kilograms. So we'll go ahead and write that down. Mass equals 58.0 kilograms. What force does the elevator floor exert on you? So first we want to find this force, and then afterwards you begin to feel heavier, and the screen now reads A equals positive 2.05 meters per second squared. And then we want to find that force. And then you come to a stop, and we want to know if we went up or down. So the first thing we're going to do is write down what we know. So we know our mass, and then we have two different accelerations. So this is two different parts here. So A1 is negative 2.10 meters per second squared. And then the acceleration changes to positive 2.05 meters per second squared. So we'll first go ahead and draw our picture. So here we are on this elevator that we woke up on. We don't know where we're at, and we don't know if we're going up or down. So we have two different forces acting here. Obviously, the weight of the person. So weight, which of course is just mg. And then there's the normal force, which is the force that the elevator floor is exerting on the person. Note that this would also be the same force that a scale would read on the elevator, since that's common in elevator problems. But it's the same as the force from the floor. So we're going to set this problem up in the same way we would do if we had a scale, right? So we're using Newton's second law. The sum of the forces here, or the net force, equals mass times the acceleration. So the two forces that are acting are N, the normal force, in the positive direction, and then the weight in the negative direction, so minus W equals MA. And for this problem, we're just going to write this as N minus mg, since we know our mass. So we're trying to find the normal force here. So all we have to do is move mg over to the other side. So we're adding mg, and then we just have basically an equation for the normal force. Normal force equals ma plus mg. You make this a little bit simpler by saying m equals a plus g. So we can just plug in our values for these two different parts. So in the first part we have a1 equals negative 2.10. So that's our first part. And our normal force is going to be the mass, 58.0 kilograms, times the acceleration, which is negative 2.10 meters per second squared. And then we have positive g. So we already accounted for the fact that weight is in the negative direction. So we're putting in positive 9.81 meters per second squared. And this is going to give us a normal force of 447 newtons. And then in the second part, we want to basically just do the same thing, but we're plugging in a different acceleration. So our normal force in the second part, so we'll call this 1 and 2. The second part is going to be 58 kilograms times positive 2.05 meters per second squared plus 9.81 meters per second squared. And that's going to give us 688 newtons. So we have our two different normal forces here. And now we have to figure out if we went up or down. So there are a couple of things we can think about here. First of all, let's just find the weight of this person. And that way we can compare it to our normal force. So weight equals mg. Now this isn't exactly necessary. You could just look at these numbers and possibly tell if you're going up or down, but we're going to go into some details just so that it's really clear about why the answer is what it is. So this is going to give us a weight of 569 newtons. So that means initially when we're feeling lighter, the normal force is less than the actual weight. And then in the second part, when we're feeling heavier, the normal force is bigger than the actual weight of the person. And that makes sense, right? You're going to feel heavier than what a scale would read is going to, is going to be higher. Whereas when you feel lighter, the scale is going to read something lower. So let's just think about the differences between going up in an elevator and going down in an elevator. So let's just remember that acceleration is actually the change in the velocity over the change in time. So that's the final velocity minus the initial velocity over delta t. So we rarely talk about the actual velocity in these elevator problems, but if we think about it, when we're going up, we're starting from rest and we're starting to accelerate upward. And when we're accelerating upward, we're starting from 0. So v initial is 0, and our v final, we're still moving upwards. So that's going to be positive. Remember, if velocity is in the opposite direction, it's going to be negative. So we have a positive v final over delta t. Okay, let's go ahead and fix this. Accelerate up. Okay, so when you're accelerating up initially, you're going to have a positive acceleration. And then if you're going up, you still have to come to a stop when you get up to the higher floor. So you're now decelerating. So the next step when you're moving up is then decelerating in the upward direction. So now you have your acceleration equals, so v final minus v initial, but our final velocity is 0, right? And our initial velocity is positive, we're still going up, but v final minus v initial over delta t is going to give us a negative acceleration, right? So 0 minus v initial is still going to be minus v initial over delta t. So that's going to result in a negative acceleration. So this is if you're going upward. However, in our problem, we initially had a negative acceleration and then a positive acceleration. So obviously we were going downward. Let's explain the difference here. So we have our elevator and our little person in the elevator, and now we're going down. So you start off by accelerating down, and you're initially at rest, so you're not moving initially. Your initial velocity is 0. So then our acceleration is going to be a negative v final because we're going downward, so it's in the negative direction. And our initial velocity was 0 over delta t. And of course, delta t is never going to be negative. That's just an amount of time. So then this is going to give us negative v final over delta t, which results in a negative acceleration. And then we're going to decelerate down. And this is resulting in a kind of double negative almost, right? So our acceleration is going to end up being positive and we're going to feel heavier, right? So for decelerating down, then our final velocity is 0. We're stopping, coming to a stop. And then our initial velocity is in the downward direction. So when we start to decelerate, we're still going down. So minus a negative v initial over delta t. So now we have a double negative here, and we're just going to have v initial over delta t. And that results in a positive acceleration. So then the answer to our question is that we were going downward, right? Because we started off with a negative acceleration and then ended up with a positive acceleration. Now, you don't necessarily have to go through all of that analysis to figure out that you are going downward. Once you get the hang of these types of problems, you know that if you're going down, you're initially going to feel lighter, and then you're decelerating downward, you're going to feel heavier. So once you kind of get that down, it's a little bit easier to just know that you're going downward because you're initially feeling lighter and then you feel heavier. And so that's kind of the way to approach these problems.